Welcome to Basic Thermodynamics class. We are discussing chapter 4 A Standard Cycles. Subtopic Otto cycle numerical problems. So we'll solve some more problems based on a Otto cycle. So before doing the problems on Otto cycle, I am once again explaining the PV diagram of the Otto cycle, because it is a very important to solve the problems. Without knowing the PV diagram and what are the process involved in the PV diagram, we can't do the problems. That's why for each class I am repeating the PV diagram and TS diagram of the Otto cycle. So this is the PV diagram, that is 1 to 2. The process represents adiabatic compression, 2 to 3 constant volume heat addition, 3 to 4 adiabatic expansion, 4 to 1 constant volume heat rejection. So here the 1 to 2 adiabatic compression, in this there is no heat transfer takes place, therefore the entropy remains constant. So in TS diagram it is clearly shown that the entropy S1 is equal to S2. Coming to the 2 to 3 process, here we are giving heat to the system at constant volume. Here we are, heat is supplying at constant volume. Here the volume remains same for the 2 and 3. V2 is equal to V3. V2 is equal to V3. We heat supplied I am representing as a QS or some Q1 also. QS or Q1. And 3 to 4 is an adiabatic. 3 to 4 is adiabatic compression, adiabatic expansion. These also no heat transfer takes place, that the entropy remains constant. Entropy S3 is equal to S4, and for the calculations of each temperature and the pressure, we will the adiabatic law holds good, that is PV power gamma is equal to constant. So for 3 and 4 we can write the relation between pressure and temperature, pressure and volume, or temperature and volume. By using these relations we can find the at particular state we can find the temperature, volume and temperature pressure. Next 4 to 1. 4 to 1 is a heat rejection at constant volume. Here the heat is rejecting. Here the heat is rejecting. So I am representing with a Q2 or QR. So for easily understand, for I am writing QR. QR. So this is a PV diagram of the Otto cycle. Next, coming to the what are the formulas used for the Otto cycle to solve the problems. First one, the compression ratio R is equal to Vc plus Vs by Vc, where Vs is equal to swept volume, we call it as a pi by 4 d square L, and Vc is the clearance volume. And in terms of a compression ratio, efficiency is equal to 1 minus 1 divided by R power gamma minus 1, where R is the compression ratio, gamma is equal to adiabatic index. So efficiency is equal to, we can write the efficiency also output by input. So what is the output here? Whatever the work done by the system is the output. So output is equal to heat supplied minus heat rejected, and input is nothing but whatever the heat is given to the system, that is heat supplied Q1. So this one is a very important. So in the last class we didn't solve the problems on this type. So now we will solve the problems on this type. So adiabatic compression 1 to 2 is a adiabatic compression. So T2 by T1 is equal to, we can write the V1 by V2 whole power gamma minus 1. So if you know the temperatures of a T1 and the compression, and R is the compression ratio, in the problem if they given the initial condition temperature and the compression ratio, by using these relation we find the temperature T2. And also if they given the initial pressure also, by using the this relation P2 by P1 is equal to V1 by V2 whole power gamma, by you can find the P2 value. So here R is the compression ratio, V1 by V2. Next, second one is a constant volume process. So here at the 2 to 3 process, we are keeping volume as a constant. Heat is supplied at the constant volume. So here the volume is constant means the pressure is directly proportional to the temperature. As the pressure increases, the temperature increases. So the process is 2 to 3. So I am writing here P2 by P3 is equal to T2 by T3. Next, heat supplied Q1 is equal to mCV T3 minus T2. Why we wrote the CV? Because here we kept as a volume as a constant. So that's why we are taking the specific heat at a constant volume. Mass, M is a mass, specific heat at constant volume, T3 minus T2. T3 minus T2. And third one, adiabatic expansion 3 to 4 T3 by T4 is equal to V4 by V3 whole power gamma minus 1. Same P3 by P4 is equal to V4 by V3. So, and fourth one is a constant volume heat rejected. So, at 1 to 4 to 1, the process is a heat rejected at constant volume process. So, P1 by P4 is equal to T1 by T4. And he can write as a heat rejected Q2 is equal to mCV T4 minus T1. So these are the formulas at each process we are using to solve the problem of Otto cycle, and we calculate the efficiency of an Otto cycle. So efficiency of by Otto cycle we can write this as W by Q. W is nothing but, if you know the Q1 and the Q2, so W is equal to Q1 by Q2 divided by Q1. Otherwise, in terms of a compression ratio, 1 minus 1 divided by R power gamma minus 1. So, in the both the ways we can find the efficiency of an Otto cycle. So, the first problem, an engine works on Otto cycle with the following data. The maximum temperature 1100 degrees centigrade, exhaust temperature 350 degrees centigrade, ambient conditions 1 bar and 30 degrees centigrade. Find compression ratio, maximum pressure and air standard efficiency. So in the problem here they given that there is a cycle is an Otto cycle, and they given the some data about the Otto cycle. So what is it? The maximum temperature. So first you have to draw the PV diagram of the Otto cycle, and you have to replace the points at each state. What are the points? 1, 2, 3, 4. So at that PV diagram where the maximum temperature occurs means by seeing the diagram we can say that the maximum temperature takes place at a point 3. So I am write the maximum temperature at a T3. And coming to the exhaust temperature. So exhaust temperature is at the T4. Exhaust means final temperature, that is the T4 350 degrees centigrade. And the ambient conditions means starting initial conditions P1 1 bar, P bar is nothing but the pressure, P1 1 bar and T1 30 degrees centigrades. So what they asked, you have to calculate the compression ratio. So it is a compression ratio R. R is equal to V1 by V2, or we can write as a V, if you know the cylinder clearance volume and the swept volume, we can calculate from using that swept volume and the clearance volume. But in the problem they didn't given the clearance volume and the swept volume. So just they mention only the temperatures. That's why we have to calculate the at each state of the point we have to calculate the temperature and the pressure and the volume. So we have to calculate the compression ratio is nothing but R is equal to V1 by V2. Next, the maximum pressure. So the maximum pressure takes place at the pressure P3. And next, air standard efficiency. If you know the compression ratio, then automatically we find the air standard efficiency by using the formula efficiency is equal to 1 minus 1 divided by R power gamma minus 1, where R is the compression ratio and gamma is an adiabatic index. So it is very important that you have to draw the PV diagram of an Otto cycle. So first draw the PV diagram of Otto cycle. So this one is the PV diagram. So PV diagram It's not the temperature, it is the pressure. Sorry. The temperature, it is the PV volume, VOL. So it represented with the V. So at each point also here the V1, V1, V2 also there, V1, V2 at point 2. So like this, T2, P2, V2, and here at point 3 also T3, P3 and T3. So we have to calculate all these pressures and temperature and the volume at each point. At each point. So here it is a V3 and V4. And we know that the 1 to 2 is adiabatic compression and 3 to 2 is a heat supplied at constant volume, and 3 to 4 is adiabatic expansion, 4 to 1 is a heat rejected at constant volume. Here the volume V2 and V3 are equal, here V1 and V4 are equal. So I am considering here, first write the given data. T3 maximum temperature. So maximum temperature occurs at T3. So 1100 degrees centigrade plus 273, 1373 Kelvin. Next T4, they given as the exhaust temperature. So exhaust takes place at this point. So T4 is equal to 350 degrees centigrade. So 350 plus 273, 623 Kelvin. Next ambient condition. So ambient condition is T1, 30 degrees centigrade. 30 degrees centigrade means 30 plus 273, 303 Kelvin, and T1, 1 bar. So we are converting the 1 bar into kilonewton per meter square. It is 100 kilonewton per meter square. So you have to find the T2, V2 and V3. V3 is no, I think no need of calculating the V3, because if you calculate the V2, we can calculate the compression ratio and next the efficiency also. And for P3, by using the 2 to 3 process, we can calculate the P3 value. P3 is the maximum pressure, Next. So we know that for the adiabatic process, adiabatic expansion process, we are considering this equation T3 by T4 is equal to 3 to 4 process. This is a 3 to 4 process. Adiabatic expansion process, that is from 3 to 4. 3 to 4. So that's why I am writing as a T3 by T4 is equal to P3 by P4 whole power gamma minus 1 divided by gamma. So these P3 by P4 we can also write as a V4 by V3 whole power gamma minus 1. So both the temperature relationship with this pressure is P3 by P4 whole power gamma minus 1 by gamma. With the volume as a we can write as a V4 by V3 whole power gamma minus 1. And V4 by V3, we can write as a, because at V1 is equal to V4 at heat rejection means 4 to 1, we know that the V4 is equal to V1. V4 is equal to, at heat rejection process we know that V4 is equal to V1, and at heat supplied at constant volume V2 is equal to V2 is V4 is equal to V1 and V2 is equal to V3, and V3 is equal to V2. V3 is equal to V2. V3 is equal to V2, and we know that the compression ratio is a V1 by V2. Compression ratio is V1 by V2. So I am writing this V4 as a V1 and V3 as a V2. So then it becomes the V1 by V2 whole power gamma minus 1. So first here I am taking the adiabatic expansion process from 3 to 4. So first I am writing the temperature and the pressure relation. T3 by T4 is equal to T3 by P4 whole power gamma minus 1 by gamma. So, these pressure equation I am writing in terms of a volume. So, V4 by V3 is the whole power gamma minus 1, and after that I am changing that V4 is equal to V1 because heat rejection takes place at constant volume. So, that V4 is equal to V1, same like that heat supplied at a constant volume is V3 is equal to V2. So, V1 by V2. V1 by V2. So, I am writing V1 by V2 as a compression ratio also, or R power gamma minus 1 also we can write, or otherwise we can write as a T2 by T1. So, these relations are very important. These relations are very important. So, these V1 by V2. If you take the process from 1 to 2, we can write T2 by T1 is equal to V2 by V1 whole power, T2 by T1 is equal to V1 by V2 whole power gamma minus 1. If you take the 1 to 2 process, so already I discussed in the formulas. If you take the 1 to 2 process, so we can write T2 by T1 is equal to, if you consider the 1 to 2 process, 1 to 2 means adiabatic compression process, T2 by T1 is equal to, T2 by T1 is equal to, V1 by V2, V1 by V2 whole power gamma minus 1 whole power gamma minus 1. So, that same I writing here also. So, first initially I consider the 3 to 4 process. From that and on simplification I got finally T3 by T4 is equal to T2 by T1. T3 by T4 is equal to T2 by T1. So, in the second class, I, while discussing the auto cycle, so I already told that this explanation that we got the T3 by T4 is equal to T2 by T1, that is equal to V1 by V2 whole power gamma minus 1. So on simplification we got that finally T3 by T4 is equal to T2 by T1. So I am once again repeating that here I am considering, so don't confuse that, I am telling once again. So here I am considering adiabatic expansion process from 3 to 4. So I am writing T3 by T4 is equal to P3 by P4 whole power gamma minus 1 divided by gamma. So that the same, so I am writing the relations of a temperature and the volume. So if you take the volume into the consider, I am writing this a T3 by T4 is equal to V4 by V3 whole power gamma minus 1, and after that come to here. So we know that V4 is equal to V1 and V3 is equal to V2. So I am converting that V4 as a V1 and V3 as a V2. So V1 by V2 whole power gamma minus 1, and these V1 by V2. If you consider the process from 1 to 2, so T2 by T1 is equal to V1 by V2 whole power gamma minus 1. So I am writing this as a T2 by T1. So after that finally T3 by T4 is equal to T2 by T1. So in the given data they given the T3 and T4 and the T1. So finally we will get the T2. Finally we will get the T2. Next, we will get the T2 also. Next, V4 by V3 is equal to V1 by V2. Already we written that V1 by V2 is nothing but the T3 by T4. T3 by T4, and this gamma minus 1 comes to this side. It becomes as a 1 divided by gamma minus 1. So, V4 by V3 or V2 by V1 is nothing but the compression ratio. Here also we can calculate that. See here, T3 by T4 is equal to V1 by V2 whole power gamma minus 1. So V1 by V2 is nothing but compression ratio, and these gamma minus 1 bring to this side, it becomes as a T3 by T4 whole power 1 divided by 1 divided by gamma minus 1. So we know the T3 value, T4 value and gamma value 1.4. So substitute all the values in the R is equal to T3 by T4 whole power 1 divided by gamma minus 1. We will get the compression ratio. So the compression ratio is 7.21. So after getting the compression ratio, we can easily find out the uh, air standard efficiency of a Otto cycle. Next, we want to calculate the maximum temperature also, second bit. So we know that the P2 by P1 is equal to R power gamma. So P2 is equal to, on simplification, P2. This P1 brings to the cross multiplication, it becomes P2 is equal to P1 into R power gamma. So 1 into 7.2 power 1.4. So it is a 15.89 bar. So in terms of a, first we will get in kilonewton per meter square, next after that it will be converted into the bar. So it is 15.89 bar. Next, pressure at the end of the compression, because P2 is equal to, at the end of the compression means P2 is 15.89, but T3, temperature at the end of compression. Next, T2 is equal to T1 into R power gamma minus 1. So we know the in the T1 they given, R we calculate in the first bit, so we will get the T2 value. So 303 into 7.21 power 1.4 minus 1. So we will get a 668 Kelvin. 668 Kelvin. Next, for the constant volume heat addition, heat addition is takes place at from 2 to 3 process. Heat addition takes place at 2 to 3 process. Here the volume is constant. So we can write P3, volume is constant means the pressure is directly proportional to the temperature. So P3 by P2 is equal to T3 by T2. P3 by P2 is equal to T3 by T2. So we want to calculate the P3. So P3 is equal to T3 by 2 into cross multiplicate this one P2 goes to the denominator. So numerator, P3 by P2 is equal to T3 by T2. So cross multiply this P2 to this side, it goes to the numerator. So P3 is equal to T3 by T2 into P2. Substitute the T3 value and T2 value and P2 value, we will get the maximum pressure at P3. So first we will get in kilonewton per meter square, because you take the pressure in, if you take the pressure in bar, you will get in terms of a bar. If you take the pressure in kilonewton per meter square, it will get in terms of a kilonewton per meter square. But we take the pressure in terms of a bar only. So we will get the answer also in terms of a bar only. So P3 is equal to 32.67 bar. Next is the maximum efficiency in the cycle is 32.67 bar. Next you have to calculate the efficiency of the Otto cycle. Efficiency of the Otto cycle is nothing but efficiency is equal to 1 minus 1 divided by R power gamma minus 1. So we know the R value, 1 minus 1 divided by 7.21 power 1.4 minus 1. 1.4 minus 1 is 0.4. So first do calculation in the bracket. After that 1 minus we will get as a 54.62 percentage. First you will get as a 0.5462. So it is a percentage means into 100. So 54.62 percentage. So this is the air standard efficiency of the Otto cycle. So I will repeat once again this problem. So this problem is important for the 5 marks question. So if you know the graph of a PV diagram and process of 1 to 2, 2 to 3, 3 to 4, 4 to 1, so then the problem is very easy. If you don't know the PV diagram, so it is a very difficult to understand that problem. So first you have to be careful about the PV diagram. So draw the PV diagram and represent the process from where to where. So first draw P on x-axis and Y on P on y-axis and V on x-axis. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. Where 1 to 2 represents the adiabatic compression and 2 to 3 represents the heat supplied at constant volume and 3 to 4 represents the adiabatic expansion and 4 to 1 represents the heat rejected at constant volume. And you have be thorough about the relations in adiabatic process. So in the second chapter onwards we are discussing that thermodynamic process. In the thermodynamic process, we are much perfect about the relations between PV or PT or TV. So 1 to 2 represents the adiabatic compression. That's why you have to write the P1 by P1 V1 whole power gamma is equal to P2 V2 gamma. There we can write the P1 by P2 is equal to V2 by V1 whole power whole gamma. Like that you have to write the relations and write the given data, and whatever the data they deem given at each point, considering that process, first you take the 1 to 2 process, next to 2 to 3 or 3 to 4, 4 to 1. If not possible, come based on the data. In this problem, first they consider the 3 to 4 process, because based on the data only we will consider the process, first which process we have to take. So here we are taking the 3 to 4 process. 3 to 4 means adiabatic expansion process. From there we have to calculate the each point, the temperature, pressure, volume. After that we have to calculate the compression ratio. After that you have to calculate the maximum pressure. Before calculating the maximum pressure also, we have to calculate the T2 also. We have to calculate the T2. So be careful while writing the expressions or the relations between any adiabatic relations. So after calculating that maximum pressure also, next calculate the A standard efficiency by using the formula 1 minus 1 divided by R power gamma minus 1. So we know the compression ratio value, simply substitute here, we will get the A standard efficiency of an auto cycle. So this problem is very important for the 5 marks question. Next problem. In an ideal Otto cycle, the air at the beginning of a isentropic compression has 1 bar and 15 degrees centigrade. The ratio of compression is 8. Heat added is 1008 kilojoule per kg during the constant volume process. Assume gamma value 1.4 and the CV value 0.714 kilojoule per kg Kelvin. So see here, in an Otto cycle, the air at the beginning of isentropic compression. So they mentioned that the problem belongs to an Otto cycle. So problem belongs to the Otto cycle. So I am highlighting the problem given about the Otto cycle. So the air at the beginning. So the air at the beginning means P1 1 bar and T1 15 degrees centigrade, and they give given the compression ratio R value as 8 or V1 by V2 as 8. Heat added means heat supplied, Q1 or Qs 1008 kilojoule per kg during constant volume process. Gamma value 1.4, CV 0.714 kilojoule per kg Kelvin. First write the given data. Determine maximum temperature, pressure in the cycle, A standard efficiency, work done per kg. So, you have to calculate the T3, P3, A standard efficiency, W, work done per kg, and heat rejected per kg of air. So, first we are write the given data. For any problem like this, first we have to, very important, you have to draw the PV diagram. So pressure, volume 1 to 2, 2 to 3, 3 to 4. So I am repeating here once again. So because you are all familiar with this pressure and volume diagram, here it is a volume, it's not the temperature. It's a volume. T1 1 bar means 100 kilonewton per meter square. T1 15 degrees centigrade 288 Kelvin, R 8 and heat supplied at constant pressure, that is Q223, or we can write as a Q1 or the QS, whatever you want. So here Q223 is a 1000 kilojoule per kg, gamma 1.4, CV is 0.714 kilojoule per kg. So for the adiabatic compression, so first I am considering the 1 to 2 process. We can write the T2 by T1 is equal to R power gamma minus 1. So you want the T2 value, that's why I am writing the cross multiplication, that we will get the T2 is equal to T1 into R power gamma minus 1. So in the data they given the T1 value and the compression ratio value, and we know that the gamma is a 1.4. So we will get as a T2 as a 661.6 Kelvin, 661.6 Kelvin. Next P2 is equal to, we can write the same formula, P2 by P1 is equal to V1 by V2 whole power gamma. So V1 by V2 is nothing but the compression ratio. So P2 is equal to P1 into R power gamma. So 100 into 8 power 1.4. So it is an 1837.92 kilonewton per meter square. P2 is equal to 1837.92 kilonewton per meter square. So after finding that, we want to calculate the maximum temperature and the pressure. So in the Otto cycle, the maximum temperature and the pressure takes place at the point 3. So we have to find the temperature T3 and pressure P3. So next we move on to the process 2 to 3. So here 2 to 3. 2 to 3 means constant volume, means here P2 by P3 is equal to T2 by T3, and in the data also they given the heat supplied at constant volume. So next step, for constant volume heat addition, we know that Q is equal to CV T3 minus T2, CV T3 minus T2. So they given the Q value, CV value, and the T2 we found it, T2 is 661.6. So substitute all the values here, we will get the T3. So after getting the T3, by using the constant volume conditions, P2 by P3 is equal to T2 by T3. So there we will find the pressure of maximum pressure of Otto cycle. So next step, 1088 is equal to 0.714 into T3 minus 662. So first bring this 0.714 into the denominator. It becomes 1008 divided by 0.714. After that minus 662 brings to this side. So it becomes as a brings to the RHS side, it becomes as a plus 662. First bring this 0.714 to the denominator. So 1008 divided by 0.714. After getting the answer, bring this minus 662 into the RHS side, it becomes plus 662. We will get the temperature T3. So T3 is equal to 2073.5 Kelvin. So if you want in the degree centigrade, simply subtract the answer with minus 273 degrees. Minus 273 we will get in terms of a degree centigrade. So 2073 minus 273, it is an 1800 degrees centigrade. So the maximum temperature of the Otto cycle is 1800 degrees centigrade. So next you have to find the maximum pressure. At 2 to 3, because volume is constant, we can write the pressure is directly proportional to the temperature. So P3 by P2 is equal to T3 by T2. P3 by P2 is equal to T3 by T2. So previously find the T3 value, in the first case we found the T2 value, and P2 value also we note by using the compression ratio value. So we will get the P3 value. So T3 is at 2073.5 divided by 662 divided by, it is no P2 into A, only into 18.38. So P3 by P2. So bring that P2 into the cross multiplication. So it becomes a T3 by T2 into P2. So P3 is equal to 76. Sorry. 57.6 bar. So here we take the P2 in terms of a bar only, that's why we got the answer in terms of only bar. So P3 maximum pressure of the Otto cycle is 57.6 bar. Next step. So we can write this as a 5760 kilonewton per meter square. In terms of a kilo means simply multiply with 100. We will get as a multiply with 1000. We will get 5760 kilonewton per meter square. A standard efficiency. So efficiency is equal to 1 minus 1 divided by r power gamma minus 1. So 1 minus 1 divided by 8 power 1.4 minus 1, it is a 0.4, we will get a 0.56. So simply it is a 56.5. Next question. Work done. They also ask the work done. Work done. Next heat rejected also. Work done is equal to, we can write, we know that the efficiency is equal to output by input. Output by input. So from that we know that the efficiency is equal to output by input. So what is the output here? Uh, Whatever the work done by the system is the output. Input is the heat supplied. So heat supplied I am writing as a QAS. So here they asked the work done. So by cross multiplication we will get the work done is equal to efficiency into heat supplied. Work done is equal to efficiency into heat supplied. So already in the data they given the heat supplied and the efficiency we got by using the compression ratio. So the work done is equal to 1008 into 0. Efficiency you have to write in terms of a not percentage. So we got the 56.5. So I am writing it like as a 0.565. 0.565. So the work done is equal to 569.52 kilojoule per kg. 569.52 kilojoule per kg. So next heat rejected. So how it is the heat rejected? So W is equal to, we know that the W is equal to Q1 minus Q2. W is equal to Q1 minus Q2. W is equal to heat supplied, whatever the amount of the heat supplied minus heat rejected. So W is equal to Q1 minus Q2. So we want the heat rejected. So bring this minus Q2 to the RHS side and the W to the LHS side. So if you bring this minus Q2 to the RHS side, it becomes a plus, and plus W bring to the LHS side, it becomes as a minus W. So I am writing this equation as a Q2 is equal to W minus Q1. So already we get the heat added as a 1008 and the work done in the previous question 569.52. So that the answer is a 438.48 kilojoule per kg. So this is the heat rejected. Next problem. An engine operating in an ideal Otto cycle has a compression ratio 8:1. At the beginning of the compression stroke, the air is at 103.5 kilonewton per meter square and 300 Kelvin. If the heat supplied is 920 kilojoule per kg of the air, calculate the maximum pressure, maximum temperature and the cycle efficiency, CV value and the gamma value. So in the previous, like the same procedure of the previous problem, so there is some change in the data only. So in the problem they told that it is an Otto cycle. So first if you know that the cycle is Otto cycle, first step you have to do is you have to draw the PV diagram. You have to draw the PV diagram and represents the points answer and write the given data. R value 8 and P1 value 103.5 kilonewton per meter square, T1 300 Kelvin, heat supplied Q1 920 kilojoule per kg. We have to calculate P3 question mark, T3 question mark, CV value and gamma value. So first write the given data. So after writing the given data, you have to consider the first process 1 to 2. So we can write the T2 by T1 is equal to V1 by V2 whole power gamma minus 1. So we know that the compression ratio is V1 by V2. So 8 power 1.4 minus 1 into T1. So they are given the T1 also, T1 as a 300. So we will get the T2 as a 689.2 Kelvin, 689.2 Kelvin, and using the adiabatic index gamma as a 1.4. Heat supplied Q1 is equal to mCV T3 minus T2. So what they given, 920 is equal to mass 1, CV value 0.718 into T3 minus 689.2. So it's on simplification. So first bring this 0.718 to this side, 920 divided by 0.718, you will get a 1281.34, and bring this minus 689 to this side, means becomes a plus 689. So it is a 1970.5 Kelvin. So where it is the maximum temperature of the Otto cycle. So after that you have to, they ask in the problem to calculate the maximum pressure also, that is nothing but the P3. So in the first process we know that the P2 by P1 is equal to V1 by V2 whole power gamma, and P1 on the data they given the P1 is a cross multiplication, so P1 into R power gamma. So P1 103.4 into 8 power 1.4, it is a 1902.24 kilonewton per meter square. Why it is here kilonewton per meter square means because we take the pressure in terms of a kilonewton per meter square. That's why the pressure is also in the pressure at point 2 also we will get in kilonewton per meter square. Next, in the problem they asked to solve the maximum pressure. So how will you get the maximum pressure? If you take the process at 2 to 3, we can write that the volume at constant, the pressure is directly proportional to the temperature. So P2 by P3 is equal to T2 by T3. So we got the P2 value, T3 value and T2 value. From using these three values we will get the maximum pressure. Next slide. So P3 by P2 is equal to T3 by T2. So we are bringing this P2 to this side. So P2 value is 1902.24 into T3 value and T2 value. So we will get the 5438.7 kilonewton per meter square, because we take the pressure in kilonewton per meter square. Next, air standard efficiency of an Otto cycle in terms of a compression ratio is, we all know that 1 minus 1 divided by R power gamma minus 1, R power gamma minus 1, it is, we get the 0.5647, so it is nothing but 56.47 percentage. This is the air standard efficiency of Otto cycle is 56.47 percentage. So I am giving one problem, you try it yourself, just I will explain, there is no solution, so just in oral I will explain, so try it yourself. An engine working on an Otto cycle has a temperature and a pressure beginning of compression as a 25 degrees centigrade and 1.5 bar respectively. Find the compression ratio if the thermal efficiency is 48%. Also find the temperature and the pressure at the end of compression. So here first you have to identify what is the process here. It is an Otto cycle. Next, what's the given data? They given as a T1 25 degrees centigrade, means convert into 273, means 25 plus 273, so 298 Kelvin, 1.5 bar. So use it in a 1.5 bar only, I am not converting it, so you will get the answer, all answers in bar only. Find the compression ratio, R value, they are asking R value, they given the thermal efficiency, so 48% is nothing but 0.48. So we know that the efficiency formula is a, efficiency, just I am writing formula only, efficiency is equal to 1 minus 1 divided by R power gamma minus 1. So they given the efficiency value. So 0.481 minus 1 divided by R power 1.4 minus 1. So bring that efficiency to this side and 1 divided by R power 0.4 to the LHS side. So 1 minus 0.48 is 0.52. So on simplification we will get the compression ratio, and also find the temperature and the pressure at the end of compression. So what they ask at the end of compression. So where the compression ends at point 2. So we have to calculate the T2 question mark and P2. T2 and P2. They given the P1 value. So first consider the 1 to 2 process. In the 1 to 2 process, we know that the P2 by P1 is equal to R power gamma minus 1. So here we know the 1.5. So here we got the compression ratio. So substitute the compression ratio value, R value, and next P1 as a 1.4, we will get the P2. Same that T2 by T1 is equal to V1 by V2 whole power gamma minus 1 by 1 divided by gamma minus 1. There also we will find the T2 value. So you know the T1 value, T1 as a 293 Kelvin and R we will get from here. So and simply if you know the relation between temperature and the compression ratio, we can calculate the temperature. So here they didn't ask the maximum temperature and the pressure. They asked only that the temperature and pressure at the end of compression. So where the compression ends, so the compression ends at the point 2. That's why you have to calculate the T2 and P2. So in the next class we will discuss about the diesel cycle and what are the operations involved in the diesel cycle. Thank you.